we are discussing multidimensional unconstrained optimization. In our previous lecture, we have talked about theory as well as example on steepest descent method. In this lecture, we will actually take up a programming exercise on steepest descent method. Let us first see what this method was all about. Recall, our goal is to find out this x star. X star is the value of x, that particular x, which will minimize this fx. So to get x star, we start from an initial guess of x0, and then we keep on iteratively updating this guess. X at k plus 1th iteration is equal to x at kth iteration plus hk dk, where hk is the step size, which is a positive scalar, and dk is the descent direction, which is a vector. Now in steepest descent method, we take dk as the negative of gradient of f at that particular point of xk, that means the current point, known point. Then hk we can calculate from line search technique, such as I can take hk that will minimize this phi h function, and phi h function is that f of xk plus h multiplied by dk. When we calculate this, then this xk as well as this dk both are known, and therefore this is a function of h only. We can use an one-dimensional optimization technique and get the value of h here. So step calculation like this at every iteration may be difficult to implement in a program. Many times that is why a constant step size is used. So let us see the problem that we are going to solve. We already started solving this problem. First we have solved them analytically and then using other methods. Finally, we have seen one iteration in steepest descent. Now we will actually see a converged solution of this particular problem. Here we are trying to minimize this function f of xy, which is x square plus twice y square minus twice xy minus twice x. This is a function of vector x, and vector x is given by two components x and y. We use this steepest descent algorithm. Xk plus 1 is xk plus hk dk, and dk will be negative of this nebula f, that is the gradient of f. Gradient of f is a column vector, and the elements there are del f del x, del f del y. If we take the derivative of this function x, we get this as 2x minus 2y minus 2 and 4y minus 2x. So first we will start from a constant step size of hk equals 0.1. And let us remember the analytical solution. The analytical minimum was -2. It would be somewhere here, and it will happen at x star 2 and y star 1. So the solution will be somewhere around here. So let's see how a computer program will implement this. Here is our computer program in Python, and you can take this program and run in any of this Python interpreter. What we are doing now, we have given a constant step size here, 0.01. We are being a little more conservative than what we should be, because we are not calculating step size, we are giving it small. And then we are trying to minimize this objective function, which is this x square plus 2y square, etc., etc. X is the 0th element of this vector x, and x1 is the 0th or first element of this vector x. Then the gradient of this, we have just calculated this 2x minus 2y minus 2, etc. So that gradient also, I am calculating both the objective function as well as the gradient using this lambda function of Python. So if I call this lambda function with a input value of x, it will give me these values. And then I take an initial guess of x, that is -1, 1. Now I enter the for loop. In this for loop, I first calculate the gradient. So gradient is the gradient function of x. X I have initialized with this -1, 1. So the gradient function will come. If the gradient is small enough, then we can actually stop the calculation and we can say the current calculation, current value of x is the best value that we can have. To check that, we are taking the norm of this gradient and we are putting that in B. That is this np.lineal norm. It gives the norm of this gradient vector. You can see that gradient is a vector here. This is np array. If this norm of course is a scalar, if that is less than epsilon, I have set this epsilon as 10 raised to minus 6. If the norm of gradient is less than 10 raised to minus 6, we will break there. That means we will accept the current solution. And if it is not, then we have to calculate a new value of x. I have started with this, but now I am calculating a new value. That would be x minus this step size, which is a constant here, multiplied by this gradient. So this negative gradient is the descent direction and step size is the amount of descent we are taking. Then we can print the results, etc., etc. Here you see that this norm of gradient, np.lineal.norm, this is an inbuilt function in Python. We are using that to calculate the norm and we are using that as a stopping criteria. Now if you run this program, you will see that this will be the output of the program. The minimum value will be -1.9999, etc. Similarly, minimum location will be this 1.9999, etc. and 0.99, etc. So you can see that these are our analytical solution. Analytical solution minimum is -2 and it happens at the point 2, 1. So you can see that we are pretty close with the analytical solution and you will get there in a matter of seconds. So now that we are here, we know that this program can be accelerated in many ways. One thing, of course, that first comes to our mind is that this step size calculation. Taking a constant step size like this is okay for now for this small program, but for complicated program, it will take very long time. So we want to have some sort of an improved step size. And we know that to get the improved step size, we have to optimize that function phi h at every iteration. The minimum of phi h will give us the step size hk. That would be our optimum hk. Calculating that is not really easy in every iteration. It will require a line search technique that will use some of the methods that we have talked before, such as golden search method. So instead, what we will do here is that we will have a partial minimization, and that is the condition we call Armijo condition. Armijo condition is very popular with steepest descent. Here we don't look at the actual minimum at every iteration. What we try to enforce that, well, this next iteration value, that means x k plus 1th iteration value, must be less than fx k, and we'll settle even if it is not going all the way up to the minimum. So we'll take a value of h such that this happens, fx k plus 1 is less than fx k, but we will not minimize the fx k plus 1. So to do so, what we do, we bring an additional parameter beta here in the algorithm, and we enforce this condition that fxk plus hdk should be less than or equal to fxk plus beta hdk. This beta is an additional scalar we are taking, and we take some constant value between 0 to 1. Usually a small value we take, and then setting this value of beta, and we will set a value of tau also within 0 and 1. We will see that what tau will do. And we start with an initial guess of h. Usually we take h equals 1, but depending upon your problem, you can vary it. H equals 1 is the most popular. So what we do now that I know h from my initial guess, and beta, I have set some value of beta. So I'll check that if this Armijo condition is satisfied or not, because I know beta, I know h, d is already known. So everything is known. I have to see that this left side and right side, comparing this left side must be less than this right side. I can check this because h is known now. Beta is something that I have assumed. If the condition is satisfied, we will go with this h equals 1. If it is not satisfied, then we will use this tau h. We have a constant tau. This tau is a constant which is between 0 and 1. We will multiply that with h and we set that as our new h. And which means that whatever the h value is, I am actually reducing it because I am multiplying with a number between 0 and 1. So I am reducing h. And then I'll check the Armijo condition once again. If it is satisfied, then we are fine. If it is not satisfied, again we will come to this step 2. This typical value of tau is 0.5. And we can see that even using this kind of an heuristic algorithm can actually accelerate our computer program substantially. So let us see how we can implement it in a computer code. This is our old computer program that we have just seen. Here you can see that I am taking this step size 0.01 and I am calculating this minimum value, location of that minimum value, and the number of iterations. If I run this code, you see that you have the result here, and the result shows that it has gone up to 1889 iteration, 1889 iteration, and it is giving the value that I was just showing, negative 1.99, and the location is 1.99.99, etc. So now we want to improve this code with a line search, and the line search here I have this improved code. Here you see that I did not give an input of the step size explicitly. What I am doing is that I am calling this line search program here. That line search will bring the step size. Otherwise it is simply the old program. There is nothing different here. So in the line search algorithm, I have set this beta is 0.001. It is super conservative. I start with step size 1. That is why this is the starting value of step size, and I take number of trials 100. Within 100 I'll have my sufficiently small step size. So then I have checked this tau equals 0.5. So when it is not satisfied, Armijo condition, the step size will be reduced to half of it. Then I have this fx1 and fx2. I am calculating left hand side and right hand side of Armijo condition. I am checking them if that is small enough. So then I return the step size to the main program here. Now let me run this case. The only difference between the previous program, which was taking this 1889, and this program is that this Armijo condition is here. So let's run this case. And you can see that it has taken 44 iterations only. It is giving very similar result. There is nothing really different in result. But the number of iterations are 44. I have plotted here the graphs. This red line shows that how we are converging. So here we are. This is our starting point. From starting point, it goes like this in a zigzag line. This is in the contour plot. This is the surface plot. And this is the contour plot. So in contour plot, you can see that it drops first. A very sharp drop, come pretty close. And then it takes a sort of a zigzag path. In fact, every path is perpendicular to the previous. That is the norm in steepest descent method. This is something that brings some limitation of steepest descent, but that's for some other discussion. So here you can see that this red line is showing us that how we are converging toward the true solution, correct solution. So now we have completed a programming exercise on steepest descent method. For your exercise, you use this method and find the value of root 2. You can use one of these programs, and in fact you can use constant step size for ease of implementation. Thank you. That's all for this lecture, and I'll see you in next class.